Today, let's take a look at vectors from an algebraic perspective. Okay, well, let's start here. So again, we start at the tail and we end at the head, but these are 2 points on the xy axes. They have xy coordinates. So what if we were to call the tail x1, y1, and the head we can call x2, y2, just to differentiate. Well, when we're identifying this vector, this is how we do it. We take the difference of the x values, but you always start at the x from the head and you subtract the x from the tail. And then you do the same thing with the y's. It's going to be y2 minus y1, and that's the name of the new vector. Now, what does that do for us? Well, let's do an example and I'll show you. Okay, here's our example. Okay, so now this vector right here, let's see what we have. Let me write that down. We have our head, so the tail is A, and the tail is going to be 2, 3. And if we look at the B value has an x of 5 and a y of 7. Now, if you do what I just did, we're going to name vector AB, okay, as such. It's going to be 5 minus 2, comma, 7 minus 3. So vector AB is equivalent to 3, oh, I just realized what I did. That is minus 3, of course, not a comma. So 7 minus 3 gave us 4. Okay, it's the difference between the two. Great, 3, 4. What does that mean? Well, let's see. What happens when we plot 3, 4? Well, 3, 4, 3, 4 is right where that red dot is. So let's draw an arrowhead. And if I were to connect that to the origin, it's supposed to be a straight line, that's what happens. Vectors can be anywhere. Remember, we talked about that, and you can translate them anywhere. Well, if I were to take my vector AB here and I were to translate it starting back at the origin, that's what this labeling does for us. It tells us where the head is. This new name for any vector is as if you were translating it back to the origin, and that's where your head is going to be. Okay, and that's it. Okay, so so that's where the vector would be located in space. But what about the length of the magnitude, which is the length of the vector? Well, keep in mind that every vector has a horizontal component along the x-axis and a vertical component along the y-axis, which creates a right triangle. You can think of any vector as the hypotenuse. So how do we find the length? Well, you can use the distance formula or Pythagorean theorem. I think I've shown you that they're the same, one and the same. If this were the hypotenuse, well, the x-axis, right, that has a length of 3, and the y-axis, well, the y goes up to 4, so that has a length of 4. So Pythagorean theorem tells us that that's going to have a length of 5. How do I know that? Well, I'm just using my Pythagorean triple. I know that 3, 4, 5s are Pythagorean triples, but let me show you how it works out. So we have x squared plus y squared equals z squared. From here on in, well, actually all the time I use z as my hypotenuse because that's the next letter. Well, if our x is 3, I have 3 squared. If y is 4, I have 4 squared. And that gives us 25 equals z squared. Z equals plus or minus the square root of 25, but because we're only dealing with distance, and distance can't be negative, you're just left with positive 5. Okay, so there's my hypotenuse, which in turn is the magnitude of our vector AB. All right, well, let's take a couple vectors now and do something with them. Let's add and subtract and all this stuff. All right, well, before I show you how to do that, we need some vectors. So let's give ourselves a vector A and a vector B. We will refer to vector A as x1, y1. And you guessed it, how about x2, y2? Now we're going to do something down here with scalar multiplication, so I'm going to say that we're going to let it be letter k. K is a very common variable for a scalar. K will be our scalar multiple. It's a scalar multiple. and it is going to be any real number. Okay? All right, we'll get to that in a minute. First addition. So if I were to ask you to take vector A plus vector B, this is how you add them. You add the x values, comma, and then you add the y values. Not too bad. That would represent the sum of vector A and B. What if I asked you to take vector A and from it subtract vector B? Let's see what we get there. Well, now we're starting with A, so we do have to start with x1 and y1. So that would be x1 minus x2, comma, y1 minus y2. And for the scalar multiplication, a scalar multiple is something you just distribute and multiply everything by. So it would be something like this. It would be asking you to say, what is k times A, or k times B? Well, let's just use k times A as our example. Well, that would look like this. K times, well, what is vector A? Vector A is x1, y1. So if you distribute, what do we get? We get k times x1, comma, k times y1. Let's do some examples. Let us take vector A, and let's assign it some values. How about 2, comma, negative 3? And vector B. I don't know, how about, 4, comma, 2. And we are going to need a scalar, and I said it could be any real number. So how about, we'll keep it simple for this. How about k equals 4? Okay, so those are our givens. For addition, let's add vector A plus vector B. Well, we said we take the sum of the x's, so I'm going to add 2 plus 4. Those are the two x values. And I'm going to add the two y values, negative 3 plus 2. And we are going to get 6, comma, negative 1. That would be the sum vector between A and B. Okay, what if we were to subtract these two? Vector A minus vector B. Well, because A, now here it doesn't matter because addition is commutative, but subtraction is not. Never forget, 3 minus 4 is not the same as 4 minus 3. So whatever vector comes first, those xy points come first. It has to be that way or else you're going to get the wrong answer. All right, so let's see. Vector A comes first. So it's going to be 2 minus a 4 and a negative 3 minus, I did it again. That should be a minus, there we go, negative 3 minus 2. Let's simplify. 2 minus 4 is negative 2. Negative 3 minus 2 is a negative 5. There is the difference between A and B. Scalar multiplication. Let's change it up this time and use vector B. What if we were to do k times vector B? That would look like, well, k is 4, and vector B is 4, comma 2. So if we distribute, you are going to get 16, comma 8. Pretty easy. Now for a unit vector. Well, a unit vector, why don't we start with the unit circle? This might make the most sense. All right, well, with the unit circle, you may remember that all the radii are 1. So if all the radii are 1, all of these are 1, which would make our xy points, blue. This one on the xy axes would have a value of 1, comma 0. This would have a value of 0, comma 1. And just to finish off these endpoints, this over here would be a negative 1 on the x and a 0 on the y, and this would be a 0 on the x and a negative 1 on the y. So those are your values around the unit circle on the quadrants, on the axes. All right, well, unit vectors, if you look at this picture over here, we associate the unit vector on the x-axis as I. Okay, the unit vector is I, and that's the little notation right there for vector, for the unit vector. Okay, we've up to this point I've shown you vector I can be written like that, but when we're dealing specifically with the unit vector has a little hat on it like that. Okay, so just so you know the notation, they're both vectors. And so if you look here, if I'm telling you the unit vector along the x-axis is I, and the unit vector has a length of 1, well then, vector I, what can I write this? Let me do it down here. Vector I, or unit vector I, if you will, is equivalent to 1, 0, because that's where the tail starts here and the head would end there. Vector j, for the same reason, vector j, unit vector j, is denoted with a 0, 1, because that's where it falls. Up here, if this were the unit circle, oh, I'm using white. How about something darker? All right, this is not a good circle, but I think you understand here. This has a length of 1, and that's I, so I has, that's where the head is, 1, 0, and j ends there. The head ends at 0, 1, so that's how you identify I and j. They're labeled by those. And then what we're going to do with these is we're going to take a vector and treat it as the sum of unit vectors. I'll show you how to add that. But right now, we're not going to get into 3D, but I just want to show you the relationship while we're right here. So let me just get rid of a couple things here. Okay. If I were to, oh wait, let me do this. 1, 2, 3, and then I can delete that. There it is. We're going to get into three-dimensional space, which is the world we live in. And we are going to talk about a unit vector k. I just want to bring that to your attention here. Just as if you have something going out that direction or that direction, you could have things coming out towards you. Okay, so vector k will be the unit vector for the z-axis. We'll get to that shortly. Now that we have an idea of what a unit vector is, let's take a vector and write it as the sum of unit vectors. All right, well, this vector right here, we'll use this one as our example. And if we just used our normal labeling system, well, that's what we did. Let's see what we got. We got 3 on the x, and we got 2 on the y, so that would be 3, 2. Okay? But I want to express this as the sum of unit vectors. So here's how we do that. On the x-axis, that orange vector right there is a unit vector. It goes to 1, 0. So the unit vector I is 1, 0. But I'm not going out there. I'm going out all the way over here to 3. So I have to take that and multiply it by 3. If I take that and multiply it by 3, you distribute, and you're going to get a 3 times a 1 and a 3 times a 0. And that's exactly where the horizontal component goes. It goes out to 3, 0. Let's look at the vertical piece now, up this way. Okay? Use green. Well, the unit vector on the y-axis goes up to 0, 1. 0, 1 is the unit vector there. But again, we're not going up there. We're actually coming all the way up here to 2. So that would, I'd have to multiply it by 2, because watch what happens when you distribute. 2 times 0 and 2 times 1. And that's exactly where the vertical component is going. It's going up to 0, 2. Now, because you're allowed to, well, here, let me just rewrite this. This right here, this equals I, so this is the same as 3 times I. And this right here is the same as j, so that's the same as 2 times j. And I'll use the little hat on top. And the sum of unit vectors, all I do is this. I'm adding those two vectors. Because remember, with the geometric vectors, I can translate these anywhere I want. If I were to take this vector and move it over here, well, it's going to have the same direction and the same magnitude, right? So that's 2j over there as well. And right over here, this one we said was 3i. So how do we add vectors? We go from the tail, here, where am I here? We go from the tail to the head, and then the tail to the head, and then the shortcut is the sum of those two vectors. So this one represented as the sum of unit vectors would be 3i plus 2j. There you have it. Let's just do one more before we wrap it up here. I want to make sure you understand this concept. Okay, so here is a new one, and I'll do this fairly quickly since we just talked about it. So the unit vector over here is 1, 0, but again, we are going, where are we going out to? What is that, 8? So we're going out to 8. So if I did 8 times the unit vector, I'm going to get 8i. And the unit vector over here goes up to the 1 right there. That would be j. But again, we're multiplying it. Where are we going? We're going up to y equals 10. So I would be multiplying it by 10. So that would be 10j. And I can translate this green vector over to here, which would then give me the sum of the unit vectors. I'm adding 8i plus 10j. I can write this one as 8i plus 10j. There you have it. Never forget the power of a video. If you missed anything or want to review it, you can. Pause, rewind, they are lovely. What are we doing tomorrow in class? My suggestion is you write this in your notes right now so you don't have to ask me. You could just open up your notebook and say, we are going to page 423. Here, I'll make it bigger for you so you can see. We are going to be doing page 423, those problems in class. See you then.